So my name is Justin Cook. I work in the Programming Environments and Models group at NERSC. And what that means is it's basically consists of all of the tools, the libraries, the compilers, communications tools, and everything that you need to make and build software and make sure that it works on these systems. So for when you're on Perlmutter, we have four main ways that you can get at software or get software for yourself to use. We use something called environment modules that you can use to get at locally installed software, including software that's installed on the host. You can pull in a container that has your software installed. We don't cover that in this, but we do have documentation of that on the website. You can compile your stuff from source on Perlmutter using the tools that we provide. Or you could use a package manager such as Conda or SPAC, or you could use a software stack like E4S. E4S meaning the exascale um, environment for supercomputing services. And again, we aren't going to cover package managers today, but we do have documentation on using those on the website and on our docs. So this slide is a little busy, but keep in mind, we're just trying to introduce you to some of these topics. And so I'm going to go through and explain it all in detail. So module is a program that modifies your environment so that you can access multiple different versions of software. If we were to just install one piece of one Python, then if someone needed an older or a newer one, we would have issues. If we install multiple versions, how does the user know how to access each one? And so in this case, we use the module command to organize the software and make it so that it just modifies the user environment so that when they say, I want this version of Python, when they call Python, that's the version they get. So in this case here, the default version of Python that's installed on the host for the host software is Python 2.7.18. And you can see your currently loaded modules with module list. And you can see that there isn't a Python module loaded right now. So if we do load a Python module, we now see that it is available in the list at number 18 here. That's highlighted in blue. And you can see that when you're on Python version now, you get the correct version of Python that you were expecting. So there are some modules that are loaded by default, and this is just so that you can make use of Perlmutter and its GPU and CPU architecture efficiently by default. The Cray PE x86 Milan targets the CPU architecture. The programming environment GNU and the GCC native 12.3 means I'm going to get GCC 12.3 as my compiler. And then the CUDA toolkit 12.2, the Cray PE Excel NVIDIA 80, and the GPU module all are things that hook into I need to program for the GPU. I want to target the A100s that Perlmutter has, and I want to make sure that I'm using CUDA aware MPI and other CUDA libraries. Now with LMOD, there's a whole bunch of commands that you can use to help you get access, find out whatever you want to do with modules. We have documentation again on the website if you need something. There's a man page for the module command. But these are the most common ones that you're going to kind of use on an everyday basis. You're going to use module list to see what you have loaded. You're going to module load or unload something if you need it or don't need it anymore. You can get help for a particular package if you don't know what it is or what it does. You can do a show on a package to see what we do when we modify your environment when we bring it in. And you can use the spider command, which is a way of searching through all of the potential modules. Module avail does not search for all possible modules. Because Perlmutter uses LMOD, it's a hierarchical system, which means If you have a certain compiler loaded, it's going to use that MPI for that compiler. There are other MPIs for other compilers, and there are other libraries that depend on other modules being loaded. And so that hierarchy will only be shown by module avail if you have the correct modules loaded. So instead, you can use module spider to search through all the possible module files. And you can also use it to figure out which modules you need to load in order to get that one. Some common examples of this are parallel netcdf, netcdf, and HDF5. So when you load a module file, this is kind of what happens. This is the module show command, and this is for Cray HDF5. It sets some internal stuff saying, hey, this is an HDF5 module. I'm going to conflict with these other modules, and here's some help information. It's going to prepend or set some environment variables, and a lot of these are in your environment that the Cray programming environment, our programming environment, uses by default that you don't need to worry about. The ones that you care about probably here are path, so that you get access to the binaries, package config path, so that if you're using package config to build your code, it'll pull in those libraries, and then LD library path. But in this case, it's not setting that. So here are some one-line code compile examples so that you can get used to compiling at NERSC. In the past, on your own machine or on an MPI cluster, you might have used GCC or MPICC to compile your code with MPI or with MPI without MPI available. In this case, since this is a Cray system, we use something called the Cray compiler wrappers. And those wrappers make use of all of those environment variables that you just saw in the previous module, so that you don't have to actually add a whole bunch of flags whenever you have your environment loaded to make use of the modules that you have loaded. It just does it for you for a vast majority of the projects and products that you're loading. So here's an example C code with MPI. It's very simple. Hello world from processor X. And to compile this, you would use the C++ hello MPI, that's CPP-O hello MPI. And the reason that you're not using GCC again is we're using the C++ compiler wrapper, which is capital C, capital C. Now here's a C code that does something similar, except this one has OpenMP in it. And this is one of the cases where you're actually going to have to set a flag when you're compiling, because OpenMP is something that you can have optionally on. Not all codes use OpenMP, and so it doesn't make sense to always turn it on like MPI if you have the module loaded. This is a GPU code with some CUDA-aware MPI. So if you're going to compile, you want to make sure that you have the GPU module loaded. You're going to want to make sure that you compile it with the CC. Again, the lowercase cc is for C, and that takes care of all of the flags again. But if you want to run, make sure you're specifying the number of GPUs with the -G, and make sure that you're using the correct queue. So again, with this CUDA-aware MPI, it's all handled in this GPU module, and that's because it's setting this environment variable here. So if you're trying to do GPU programming and you're trying to use MPI and you want your MPI to be CUDA aware, you must make sure that this GPU module is loaded when you're doing this type of stuff. It's loaded by default, and if you don't want to use it, you can swap from the GPU to the CPU module. But most people are using GPUs for most of their codes. These are some good to know compiler settings for each one of the compilers that we have available. If you want to know more information, there's man pages at the bottom or a link to the documentation. The top line is for default optimizations. That's a dash capital O, 0, 0, and 1 in the three letters. For the second line, it's using aggressive optimization, and that can be problematic for some codes because it might produce incorrect results. But those are dash O capital O fast, O4 and fast. Enabling OpenMP, which again is not done by default. You can do that with the different options here. If you want to enable something called OpenACC, which is similar to OpenMP, but for a GPU programming model, that's on the NVIDIA compiler. If you want to enable debugging, such that you want to use a debugger or a performance tool or something like that, you would use -G with the default optimization. And if you want to get some verbose information about what's happening when you're compiling your code, where things are happening, what's being linked in, and any warnings and things like that, then you can use the verbose mode. So the compiler wrappers are just a bunch of things that pull in other flags from all the modules and the environment settings that you have. And this is kind of what it's doing under the hood. If you reset this cray.pe verbose flag to the compiler wrapper, you can see that under the hood, it's doing a whole bunch of things based on your compiler you're using, what in modules you have loaded, and some other cray defaults, right? If you have the CUDA toolkit loaded, it's going to load all those opt NVIDIA. It's going to link in all of those or include all those or includes. It's doing the same thing for mpitch and libsci. It's setting your default targets. It's making sure to use the right version of GCC, or in this case, G++. And there's a whole bunch more things that you can do. So you can take a look at that at any code that you want in the future. There are man pages for all of these individual wrappers where you can see other ways to see this information. So if you're curious, you can look there. And again, like I said, it includes a lot of information. This is all based on the different modules you have loaded, though. You have your targeting module here. You have your libsci here. You have a whole bunch of stuff here and here for your CUDA toolkit. You have your mpitch and libsci again right here. You have xpmem, and you have a whole bunch of as neededs, which means, hey, compile, link this in, but only if the users actually need it and the code actually needs these symbols. So all the compiler wrappers work with all of the programming environments. So it's not just a GCC option. You can also use the NVIDIA compiler or the Intel compiler, and they're going to tell you the information that is being done with each one of those as well. This is just a list of what compilers you're getting based upon which wrapper you're using and which program environment that you're using. You have your GNU, your NVIDIA, your Intel, and your Cray. The reason we include Intel, even though we don't have Intel CPUs, is because the Intel compiler is sometimes better, especially in the case for some versions of Fortran codes. And so we include that as well. NVIDIA is using a PGI under the hood. That's an older compiler. And Cray is using an LLVM Clang and Flang style for Fortran. So again, all of the linking and all of the libraries come from your module environment, and they get linked in automatically by the wrappers. So if you just have the modules loaded, you are going to get MPI, LAPACK, BLAS, ScalaPack, all of your targeting, all of your GPU stuff by default. You don't got to put in the flags. You don't have to do anything else. There are other modules such as HDF5 and FFTW that will be linked in automatically, but you need to load the module first. Again, this LAPACK, ScalaPack, BLAS, and etc. are usually included in Cray libsci. Libsci has different ways of being built and used such that it can be optimized for GPU, CPU, MPI, OpenMP, all the different models. Whatever model you choose, Cray libsci has a mode for, and it implements all of the LAPACK, Scala BLAS, and other scientific APIs. Now, for build systems, it's pretty easy to adapt to using these wrappers. You just need to make sure that you're setting the correct environment variables or you're setting the correct variables for your build system. In the case of auto tools, you're going to set CC, CXX, and FCC or FC to each one of the correct versions of your wrapper. And in this case, we're just setting it to which CC because we want the default. In configure, you just do the same thing, except that for F77, you're setting it for the exact same wrapper for Fortran anyway, because it implements both F77 and newer Fortran standards. Again, if you need more information, we have some build tools documentation for both AutoConf, Auto Tools, and for CMake. So if you want to compile an AutoConf or an Auto Tools system, the GNU GSL or the GNU Scientific Library is a good example of how this works. You're going to run configure just how you did in the previous step and make sure that you're using the correct compiler wrappers. You can do a make with the J8 parallel if you want, and then you can make install. libxc is another scientific library that a lot of users commonly use. And again, this is one is CMake based. And so you just make sure that you run CMake, excuse me, to get the correct settings. Then you're going to go ahead and build and install with CMake as normal. So again, the best practices here is if you need to look for all of the modules and you want to search, make sure to use Module Spider. Modules are the software we use to make sure that you can get all of the software available on the system and use the correct versions. Make sure you use the compiler wrappers with your programming environment modules so that you're getting all of the flags and setting all of the things correctly so you can best optimize and best use the architecture. Error messages and man files and docs. If you get an error, check the man direct files. If you get an error, check the directory for our documentation. Check Google. If you have further questions or your error message you can't figure out, feel free to open up a help ticket on help.nersc.gov. We also have a Slack for NERSC users. A lot of users have come across a lot of these problems, and sometimes they can be helpful as well. And that's all.
Any questions for Justin? So Justin is one of the staff members in a different group from user engagement, although he works heavily with us. Justin, what do you enjoy most about your role and working at NERSC?
I'm one of the few that are not a PhD. And so I get to learn from a lot of people who are a lot smarter than me. Not being the one person who's, you don't want to be the smartest person in the room. You always want to make sure you're in a room full of smarter people. I also like solving big, complicated problems that other people can't solve and making sure that users can just get their work done and go home at a reasonable hour, right? That's all we want to do. We just want to get our work home so we can go home and be happy. We don't want to be stuck working on things and paddling the boat for too many hours.
Words to live by. Definitely. Okay, did anyone else have any questions for Justin? Thank you so much for letting the users know all of the different available options and compilers and things that are available.